Dale, you can go ahead. Dale, you
Okay.
can introduce.
Okay, welcome everyone to the Fellowship of the Ring. That our speaker today is Jan Draisma, who will speak on new instances of equivariant noetherianity.
Thanks so much. Many thanks for the invitation to speak in this illustrious seminar series. So my talk is about rings that are not Noetherian, but become Noetherian modulo the action of a very large group. This is a topic that I've been working on for quite a while now. Originally, I was motivated by questions from about certain statistical models and questions about tensor decomposition, but in the course of my work and collaborations with many wonderful people, I realized that versions of this equivariant Noetherianity are relevant to other areas. Of course, commutative algebra, but also algebraic combinatorics and maybe representation stability. And well, basically today I just want to give a bunch of examples of this. And of course, I'm very curious to hear if people have encountered other examples or have conjectures about other examples. So let me just get going. So the topic is the following. We have a group or sometimes monoid G, which acts on a ring R. And this action is then by endomorphisms. And of course, if G happens to be a group, then it's automatically an action by automorphisms. And then we say that R is G Noetherian. If every chain of ideals and in fact G stable ideals is eventually constant. Right, so it's the usual notion of Noetherianity, except that we only look at ideals that are preserved by this group. And sometimes we will ask for a slightly weaker notion, so we will call it topologically G Noetherian if the same holds, but only for chains of radical ideals. And of course, again, G stable ideals. Okay, and we're going to use the same terminology for the spectrum. So the spectrum, which is an affine scheme, is Noetherian if every chain of closed subschemes stabilizes, and topologically Noetherian if that same holds for reduced subschemes. So let me right away give you an example, which is an old theorem due to Daniel Cohen originally, and then it was rediscovered by Aschenbrenner and Hiller. Which is, you take, let's say, a Noetherian ring, and you take the ring R, which is B, and then x1, x2, and so on. So this is a polynomial ring over B in infinitely many indeterminants, x1, x2, and so on. And G is the symmetric group, the infinite symmetric group, which I'll write as sim. That is the union over all n of the symmetric group of the numbers 1 up to n. And this acts, well, it doesn't do anything on the coefficients in B, but it acts on xi by the natural formula like this, right? And the statement is that R is G Noetherian. It's quite interesting. So Cohen was interested in such a statement. He was working on universal algebra, and he needed this statement to show that that every variety of metabelian groups, so two-step nilpotent groups, is defined by finitely many axioms. I think roughly that was the statement that he proved. Aschenbrenner and Hiller, I'm not quite sure what their motivation was to work on this, but later Hiller and Sullivan worked on a generalization, which in fact was also already discovered by Cohen about 20 years later, and Hiller and Sullivan discovered this 2 years later than Aschenbrenner and Hiller, which is the same thing. But now R is Bxij, where I runs through the numbers 1 up to k, and j runs through the natural numbers. And so the action of a permutation on xij is just xi by j, right? So the permutation doesn't act on the first index. So this is k rows of infinitely many variables, and the same statement holds. And in this case, I'm not quite sure what Cohen's motivation was, but Hiller and Sullivan's motivation was in algebraic statistics. They were interested in so-called hierarchical models. So these are models that involve a simplicial complex, but let me just give the one of the easiest examples of this. So you imagine that you have some random variables, 3 of them in this case, and each of them can take a finite set of values, and the probability that you see the value I at this random variable, and the value j at this random variable, and the value k at this random variable. So let me write it as probability of I, j, k. This is equal to some parameter in this particular model that depends only on I and j, and some other parameter that depends only on j and k, and some other parameter that depends only on I and k. So in this case, the simplicial complex that I'm talking about is just the edges of this triangle, but not the triangle itself. And then there is some normalizing constant, which usually we don't care about. And so what they were interested in is the polynomial relations, or the binomial relations among these probabilities, as some number of the state spaces of these random variables tend to infinity. So for instance, if this I runs through the numbers 1 up to n1, and j runs through the numbers 1 up to n2, and k runs through the numbers 1 up to n3. And for instance, you say, well, I keep n1 and n2 fixed, but I let this set n3 go to infinity. Can I show that in some sense these binomial relations among these probabilities stabilize? And more precisely, is it true that from some point on I have all the generators of these binomial relations? I just have to apply permutations on the numbers 1 up to n3 to get the new ones as n3 grows. And so in this particular case, that turns out to be true. And what they showed is, quite generally, if you have a simplicial complex and the state spaces that you let tend to infinity form an independent set in the simplicial complex, in the sense that there's no simplex that contains more than one of them, then this kind of stabilizing behavior always happens. And they needed this theorem about this polynomial ring for that. Okay. Now here's a fun. So far I've given examples of things that are actually Noetherian, not just topologically Noetherian. And there's a fun corollary which works in characteristic 0 but does not work in positive characteristics. So let me mention that. So if K is a field of characteristic 0, then you can take the same ring that we had before. So by this I mean this ring over here, now you see this is a ring of a polynomial ring in K rows of infinitely many variables, and on this ring acts another group, namely SLK. Just by, well, you imagine that you take that these variables represent entries of a K by infinite matrix, and you multiply this matrix from the left with a determinant 1 matrix, and this of course commutes with permuting the columns in this matrix. And so then you can wonder, well, what about the invariant ring R to the SLK? So this is just the ring that is generated by all the K by K determinants, the subring of R that is generated by all the K by K determinants of this K by infinite matrix. And if the characteristic of K is equal to 0, then this turns out to be, again, sim-Noetherian. And the proof just uses the fact that this is true without taking these invariants, and then using the Reynolds operator from classical invariant theory. And so that makes you wonder whether a similar statement is true if the characteristic is not 0, and it turns out it isn't in general. So there's a beautiful example due to Alexei Krasilnikov, which says that if you take little k is equal to 2 and you take the characteristic of the field to be equal to 2, then this particular ring R to the SL2 now, so it's just a ring of 2 by 2 determinants of a 2 by infinite matrix, or if you want, it's the affine coordinate ring of the Grassmannian of 2 spaces of a infinite dimensional space. This ring is not sim-Noetherian, but it is still topologically so. Yeah, so if you're only interested in reduced closed subsets of its spectrum that are stable under the infinite symmetric group, the descending chains of such closed subsets still stabilize. The second statement is quite an easy statement, but the example of Krasilnikov is quite clever and was inspired by certain non-finiteness results in having to do with Lie algebras. Let me not go into that now. Okay, so now we have like an example of a sim-Noetherian ring, an example of something that is not sim-Noetherian but still topologically so. Let me give a non-example of both. So if you make the ring even bigger, so let's say R is K Xij, where now I and j both run through the natural numbers. And now, well, you have a choice of groups. So for instance, what you can do is you can still have the symmetric group acting, and then pi Xij is equal to x pi I pi j. Or you can have two copies of the symmetric group acting, one on the first index and one on the second index. And it turns out that this is not topologically sim-Noetherian, and neither topologically sim times sim-Noetherian. Yeah, so this is a kind of a too big ring for this group to act on in a way that makes it Noetherian. Right. Are there any questions about this so far? I think all of this is fairly easy and straightforward, but if anything is unclear, please.
Yeah, I haven't seen any chats.
Oh, okay, very good.
Coming up on chats, so.
Okay. I'll have more
for now anyway.
Okay. I'll have more complicated examples later. So this non-example leads to a natural question, namely, well, we have this space. Is it maybe a Noetherian under a bigger group? And the answer turns out to be yes. So this R becomes an example. So this R, by this I mean this guy over here. This is GL times GL Noetherian. Let me say what that means. At least if the characteristic of the field is equal to 0. Actually, I don't know if it is true when the characteristic is positive. That it doesn't mean that no one knows, and maybe it's not very difficult either. But at least the arguments that go into the proof that this is GL times GL Noetherian don't carry over directly. And so I have to tell you what this means. So GL, first of all, is the union over all n of GL n of k. And then the action here is given by left and right multiplication. So let me just give the action on the spectrum, so to say. If you take a matrix, it's a point of the spectrum of this ring, then the action is like G A H transposed. And the reason why it is GL times GL Noetherian in characteristic 0, at least, is that we know quite precisely what are all the highest weight vectors in the coordinate ring, in this ring, whereby highest weight vectors, I mean vectors that are stable under, say, upper triangular matrices times upper triangular matrices. And so we have a very good understanding of how this ring decomposes as a direct sum of representations, and essentially, and we also know for one representation which representations are in the ideal generated by it, and then it becomes a kind of combinatorial game to show that it is Noetherian. It's not very difficult, but very nice. And well, since in characteristic positive you have to watch out with well, things are not semi-simple, and highest weight theory is not quite as nice as it is in characteristic 0. I actually don't know whether this ring is GL times GL Noetherian, but it is topologically so, even in positive characteristic. Now, I wanted to mention this example because in this case, actually, something much stronger holds, and this is a theorem due to Nakpal and Sam and Snowden, which is that, well, you know, in just classical, say, basic commutative algebra, if you have a finitely generated module over a Noetherian ring, then it is automatically Noetherian. In this equivariant setting, that is not obvious, and in fact not always true. So if you have a module that is finitely generated so if you have a finitely generated R module for this particular R, which has a compatible action of GL times GL, then in general, in such settings, you don't know whether it is Noetherian itself, but in this case it is for this particular R. So here, even Noetherian, well, let me say it like this, finitely generated Yeah, when I say finitely generated, maybe I should be a bit more careful. So I guess I want to say something like a finitely generated R star GL module or so. What I mean, it's really an R module, but it has a compatible action of GL, and it is finitely generated on them under them jointly. Is Noetherian. And so there's a very small list of cases where we know that this is the case, and this is one. Sorry, GL times GL, I need to say here. So there's 2 copies of GL here. 1 copy is not enough. Okay. Right. So now let's go up in dimension of tensors. So here, the spectrum of R is the space of matrices, and you might wonder, do we have similar statements for spaces of 3-dimensional tensors and 4-dimensional tensors, or symmetric powers or alternating powers and so on? And it turns out, at least at a topological level, we do have such examples. So let me say something about that. So spaces coming from polynomial functors. So let's assume that we have an infinite field, and we have VEC is the category of finite dimensional vector spaces. Over this field. And then a polynomial functor, so is just a functor that goes from VEC to VEC. Let's say polynomial of degree at most d. If, well, it should be a functor. And second, whenever you have 2 vector spaces U and V, then the map that goes from Hom U, V into Hom PU, PV should be a polynomial map. It's a polynomial map. Map whose components, let's say with components of degree at most d. Yeah, so in other words, if I choose bases in these finite dimensional vector spaces, then every coordinate function on the right is a polynomial of degree at most d, and the coordinate functions on the left. So to give you a feeling for this, so if the characteristic of our field is equal to 0, then it follows that such a polynomial functor of degree at most d is a direct sum of Schur functors, a finite direct sum. Finite because I'm looking at finite dimensional vector spaces, direct sum of Schur functors. Yeah, so we know precisely what they are in that case. If the characteristic is positive, it's more complicated. The irreducible ones have been classified, but how they are, you know, what the composition series can look like and how they can be connected is more complicated. In any case, when you have such a polynomial functor, you can construct a space, which maybe I'll call P infinity, which is just the inverse limit over all n of P of k to the n, where the map from k to the n plus 1 to k to the n is the natural one. Just forgetting the last coordinate, and then since P is a functor, you automatically get a linear map from this space to this space, and I take the inverse limit of these. And well, strictly speaking, this is just a uncountable dimensional vector space, but I'm secretly thinking of P infinity as the inverse limit of these spaces thought of as affine spaces. So it's P infinity is the spectrum of some ring, and this ring I will denote by K of P infinity, and this is just the limit in the opposite direction of the, let's say, well, let's maybe be more precise here, of the symmetric algebra of P of K to the n star or something. Yeah. And so now this gives a lot of examples. Let me just, to give you an example, well, one example in a sense we already saw, namely if P of V is equal to V tensor V, then P infinity is just the space of n by n matrices. And another example would be that P of V is the third symmetric power of V, and then P of infinity would be infinite cubics. So things that look like let's say A111 times x1 cubed plus A112 times x1 squared times x2 plus, and so on, and all all countably many variables x1, x2, and so on appear. Yeah. Sorry for that. We have a lamp that we have a clock that makes bird sounds at the entire hour. Okay, and so now the theorem is the following. So I proved this a few years ago, which is that this particular ring K of P infinity, well, there's an action on it by GL, because well, as I said, we have these maps over here, and well, the map from K to the n plus 1 to K to the n, it's just forgetting the last coordinate, and this is equivariant with respect to the GLN. And so if you take this union of all these, well, if you take the inverse limit of all these spaces, then the union of all the GLN is going to act on it, and similarly for the coordinate ring. This is in fact GL Noetherian. Well, I wish that were true, but so this is topologically GL Noetherian. GL Noetherian, and it is wide open whether this is also true in a ring theoretic sense. So and so even in the case of characteristic zero, where maybe one might hope to use more representation theory or classical invariant theory, we have no idea how to approach this problem. So what this means in particular is, for instance, that every closed GL infinity GL stable subset of the space of all infinite cubics that I wrote over here is defined by finitely many equations.
Jan, there's a question that just came in from Sasha Pevsner, that it's on the chat, that they ask if there are also maps Kn to Kn plus 1. What happens or goes wrong if we try to take the limits in the other direction?
Yeah, it's a good question. So I must admit, I've never thought very hard about the topological space that you get like this. So certainly you get a kind of a dense subspace of this inverse limit. Yeah, I've never thought very hard about its Noetherianity or non-Noetherianity. It's a good question. Somehow let me give another answer to this. In applications, I often don't think so much about this infinite dimensional space, rather than about a variety, a finite dimensional variety X of V that lives in P of V and is preserved under linear maps coming from linear maps between vector spaces. Yeah, so if you have a phi from U to V, then there's the P of phi that goes from P of U to P of V, and it should map X of U into X of V. And so it's like functorial, sub varieties of these polynomial functors. And my original motivation to study these infinite dimensional spaces was to prove that these functorial structures were Noetherian. But it's a good question. I haven't thought very hard about it. Thanks.
Thank you.
Okay. So right, so now we have a large class of at least topologically GL Noetherian spaces. Well, we have given these a name, so we just call them a GL variety. So that is precisely what I have here. It is a GL stable closed subvariety, closed and reduced subvariety of some P infinity, where P is a polynomial functor of some finite degree. These form a category in which the morphisms are just morphisms of varieties that are also GL equivariant. There are alternative definitions of this. It's the spectrum of a reduced ring, which is itself a polynomial GL representation and finitely generated by finitely many GL orbits of elements. So this turns out to be quite a nice category, especially in the setting of characteristic zero, but I'll get to that in a moment. Let me just give a typical example of such a GL variety. Well, in fact, in the two examples that I mentioned before, namely V tensor V, so in V tensor V, you can have things like, well, symmetric tensors or skew symmetric tensors, or things like rank at most 10 or so. That would be a typical, this is the space of all infinite matrices of rank at most 10. That is a GL stable closed subvariety. And in the other case that I mentioned, so in S3 infinity, I guess is the notation, you could have things like this. You take a map, you fix some number R, and you take a map that goes from S2 infinity times S1 infinity into S3 infinity. And in fact, each of these to the power R here. And what it does is you take R quadrics and R linear forms, and you map it to the sum for I is 1 up to R of Qi times Li. It turns out that the image of this is a closed sub-scheme of S3 infinity, and this is a typical example of such a GL variety. So the elements here are called cubics of slice rank at most R. So that's the terminology that we have here. And now there's actually a very nice theorem that precedes the theorem that I mentioned earlier, due to Derksen, Effermont, and Snowden. which says that any, let's say, GL variety X inside S3 infinity, which is not the entire space, is contained in the image of one of these maps over here. The image of alpha R. So let me call this map alpha R for some R. So in other words, if you have a proper closed GL stable sub-variety of infinite cubics, then inside there the slice rank has a uniform upper bound. And you can imagine how you can use, and in fact how they used this to prove this Noetherianity statement in the case of cubics. Namely, well, you know, you have a descending chain of closed subsets, closed reduced subsets, and GL stable. And well, you know, either it is constant in the entire space, or immediately it drops to some finite slice rank, and then you can take the pre-image of such a closed subset space in this source over here. And if for some reason you already know that that is Noetherian itself, which they did, then that implies Noetherianity for S3 infinity. Okay. So for S3 this was already known, but then I generalized that to other polynomial functors. Now since then, Arthur Big, whom I saw in the audience before, and I and Egermond and Snowden have studied these GL varieties in much more greater generality, much more detail than just proving this Noetherianity statement. So for instance, we showed that that there is a version of Chevalet's theorem for them, and we have shown that these GL varieties are always unirational, at least in the GL direction. So they admit a dominant GL equivariant morphism from a space that is of the form some finite dimensional affine variety, which may be, of course, not rational or not unirational, but times an infinite dimensional space, linear space coming from a polynomial functor. So so there's a kind of a finite complexity in these varieties. Okay, well, I wanted to say something about new instances, and I have another 10 minutes left. So let me tell you about those new instances. So the first instance was motivated by the following question. We have now seen results for the infinite symmetric group. Yeah, namely, basically what we have seen is that if the infinite symmetric group acts on x to the n, where this is a finite dimensional affine variety, yeah, that means that it is a closed subset of some k-dimensional space, and then you can think of x to the n as sitting in this space of k by infinite matrices, and then it follows that x to the n is sim-Noetherian, right? That's one statement that we've seen. And the other statement that we've seen is that GL varieties are GL Noetherian. And so it makes sense to wonder whether there is a kind of common generalization of these two statements, and there is. So the new theorem that I wanted to mention is due to Christopher Chiu, Alessandro Danelon, and then Rob Egermond and Azar Farouk. And it says that if the characteristic of the field is equal to 0 at least, then for any GL variety, x, x to the power n is sim times GL Noetherian. Well, topologically so. So topologically sim times GL Noetherian. Yeah, so what this means is, well, this is the space of infinite. For instance, if X is the space of infinite by infinite matrices, then this is the space of infinite sequences of infinite by infinite matrices, and the group GL acts like it did before by G and G transposed on the left and right, and on each of these matrices simultaneously, and the symmetric group permutes them. Actually, I wanted to give one remark about this theorem, because what we do is to prove this is to kind of cover closed subsets of such a x to the n by certain simpler objects, and let me explain that by means of an example. So first of all, we actually prove something that is stronger than this, namely that if you have k GL varieties and you take their product and each of them you do to the power n, then this is sim to the power k times GL Noetherian. So the previous statement is this statement with k is equal to 1. And it turns out that well, at least the way we prove the previous theorem, there's no way around, no way to prove this without proving this more general statement. And I can try to explain why. Namely, if you take x is equal to p infinity, where p of v is equal to v tensor v. Yeah, so that means very concretely, x to the power n is then the set of all sequences of matrices A1, A2, and so on, infinite by infinite matrices. Then there's a closed subset of this, which I'll call Y, which is the set of such sequences where for all I, AI is either skew symmetric or symmetric. Okay. So this is certainly a closed subset of x to the infinity, and it is also stable under the infinite symmetric group and under GL. And now the idea is that such a Y we can cover in a certain well-defined sense. Let me put an arrow, but with quotation marks here, because I need to explain precisely what I mean by this. But this is covered in a sense that we establish in this paper by S2 infinity to the power n times wedge 2 infinity to the power n. Okay, so well, it's not so surprising, right? You just put all the symmetric matrices first and then all the skew symmetric matrices, and you permute them among each other only. But basically our proof works via this unirationality theorem that I mentioned before, and that's actually where we need that the characteristic of this field is equal to 0, because we don't know the precise analog of that statement in positive characteristic yet. Okay, so this is the first example I wanted to, new instance of equivariant Noetherianity I wanted to mention. The second one is more recent work with Andreas Blatter and Philip Rupniewski. And what this says is it's almost the same theorem that I mentioned earlier about polynomial functors, but now K is a finite field, so K is FQ, and P from vec to vec is just any finite length representation. And now the ring that I will call again K of P infinity, but it is no longer such an algebraic object as it was before. It is just the union over all n of all k-valued functions on P of k to the n. Okay. This looks a little bit ugly, but every P of k to the n is a space. You just look at all the k-valued functions on it, and then take the union over all n. And it turns out that this is, well, this is GL Noetherian, we think. So this is certainly true if the field has at least 3 elements, and probably also if the field has 2 elements. But for this, right now, we have to depend on an argument that Antoine Touzé gave us, which we still have to try to understand completely. So what's certainly true is that it's a Noetherian under a monoid, namely the union of all the endomorphisms of k to the n, rather the union of all the GLNs. Now I still have 2 minutes left, and I wanted to mention one fun corollary of this fact, which I think is a very remarkable property of polynomials over a finite field. So if you fix any degree d, and you take any sequence of polynomials, of homogeneous polynomials of degree d, let's say f1, f2, and so on. And now they're really polynomials. So no infinite series or so, but just polynomials, each infinitely many variables. Then there exists an I less than j, such that fj, well, let me say, by a linear variable substitution reduces to fi. Yeah. Now, this linear variable substitution, of course, need not be invertible or so. You're allowed to set variables equal to 0 or variables equal to linearly dependent combinations of variables. But so if you take any sequence of homogeneous polynomials of some fixed degree d, then eventually you will find two such that one is a specialization of the other. And this is not true just for polynomials, but in fact for elements in some general such finite length functor from vec to vec. If you think about it, if d is equal to 2, this is a very easy statement because quadratic forms are over a finite field are just classified by their rank and by by whether the Gram determinant is a square or not. But as soon as the degree is equal to 3 or larger, I think this is a very remarkable fact. Okay, I think my time is up, and these were also the new instances of equivariant Noetherianity that I wanted to tell you about. So once again, if you've encountered or conjecture similar finiteness results in commutative algebra or elsewhere, I would love to hear about them. Thanks a lot.
Yeah, thank you, Jan. Let's thank Jan for his wonderful talk. Are there any questions? Have you somehow considered, is it tractable at all to say anything with this in characteristic P? That it seems like other than counterexamples.
Yeah,
very
well,
difficult perhaps.
It's difficult. So well, so this theorem, original theorem about topological Noetherianity for polynomial functors. Let me see where it is. Sorry. So this theorem is true also in characteristic P. but it's only a topological statement. We don't know whether it is true in a ring theoretic sense, even in characteristic zero. Right. Some other statements, like I mentioned these. I mentioned this Noetherianity. This unirationality result. This works somehow like this. That well, the proof of this Noetherianity statement goes like you show that if you have a GL variety, then you can always find a function on it with the property that if you invert that function and then keep the coordinates fixed where it lives, so you only act with matrices that do something with, say, the coordinates from 100 on, then this becomes of the form a finite dimensional variety times a polynomial functor. So that's how the proof of that theorem works. And that essentially works in characteristic P as well, except that that this map that goes to this product of a finite dimensional variety times a polynomial functor is, well, it has some, Frobenius in it. So so in characteristic zero, this is then just an isomorphism of this open subset to this product. But in positive characteristic, you would have to invert Frobenius to make this into an isomorphism. So I think if you formally invert Frobenius in this category of GL varieties in characteristic P, then most of the theorems that we have in characteristic zero are still true. But it's a slightly messier category for me to work in.
Yeah, it sounds, this seems like a very interesting direction to pursue.
I agree. Yeah.
Are there any other questions? Well, in that case, let's
Yes, one more question.
thank Jan again for his very nice talk.
Actually, Dale, there's one more question.
Yeah, I just wanted to ask one more question. Perhaps not a great question, a cheap shot, as it were. Is there any value in looking, say, at Giartinian equivariance for just some sort of stability for an Artinian property? The reason I ask this is because say you're really in love with the integers, right? And every theorem you prove has to have the integers, right? If you're looking at Noetherianity, then this G Noetherianity is kind of trivial, right? Because, okay, the integers, they're Noetherian. Well, they're going to be G Noetherian as well, no matter what. But the integers are not Artinian. So say you want to look at Z of X, right? You can come up with some sort of obvious action of the integers on Z of X, right? And you could ask, well, what conditions do you get G-Artinian in such a setup? I don't really know if it's worth asking this at all, but I was kind of wondering.
I'm sure it's worth asking. It's just, well, as I mentioned, my original motivation came from problems where Noetherianity was asked for. So this is what I worked on. But it's certainly a good question. There's nothing I know off the top of my head. I remember at some point a discussion with Johannes Nikes when we were thinking, so, if you have a finite dimensional variety, then there's this thing called the arc space of it. And there's a group of reparameterizations acting on it. And he asked, is this Noetherian? And then we quickly figured out that it wasn't. And then he asked, is this Artinian? And then I don't remember what came out of that. So I think it's a good question. It's just not something I have thought very hard about.
Awesome. Thank you.
You're welcome.
Are there any more questions? Okay, I'm not seeing anybody. So
actually, could I just very quickly ask has anyone worked on when the group is the cyclic group instead of the entire symmetric group? Or I don't know if there would be any application where that would be interesting.
Just the
But-
like what do you mean by the infinite? Like just infinite cyclic or?
Oh, I see.
Um,
Oh, I see. They don't fit together anymore.
Yeah.
Yeah.
Exactly. You
Okay.
do need a kind of infinite group. I mean, of course, people have worked on things like where there's a shift or so.
Yeah. Okay.
In fact, these theorems about neutrality for the symmetric group are usually proved by kind of a Grobner basis argument where you work with the monoid of increasing functions from the natural numbers to the natural numbers instead. But just the cyclic group, I don't know any instance where that makes something Noetherian that wasn't already.
Okay. Thank you.
Thanks.
Any more
Maybe just one more remark about, so it makes perfect sense to ask for smaller groups, right? And so in fact, it is true that every algebraic infinite algebraic representation of the orthogonal group is also Noetherian in the same way, and for the symplectic group the same, and also GL so polynomial representations are those where you don't divide by the determinant, but you can have conjugation and things like that. And then the same Noetherianity statements are also true. And this is all work by Andrew Snowden and Rob Egermond.
Any more questions? Okay, I think so. Let's thank Jan again for his talk.
Thank you.
And I guess we end now, I believe.